In this part of the lesson, we look at Mathematica's abilities to analyze natural language at a variety of scales, ranging from characters and words, pieces of words, up through sentences to the meanings of parts and wholes of sentences. Let's start with character frequencies. I'm going to get a list of common English words. That's stored in the single common English words. There are about 40,000 of them. Now, we've worked a lot with word frequencies and n-gram frequencies, but character frequencies can be quite interesting too. So for example, if we were to count the letters in these words, we see that E is the most common letter in this collection of English words, I, next most common, A, and so on down through J. If we focus our attention, however, on the beginnings of words or the ends of words, of course we see different distributions. So if we look at the first characters, we find that S is the most common character to begin these words, then C and P. So consonants, if we look at the last characters, and again do a reverse sort, we see that E is the most frequent last character in common English words, Y the next most frequent, D. Continuing on down, only one word in this list has Q as its last character. Now, just as we looked at word bigrams and trigrams, we can also look at n-gram sequences of characters. So if we go through here and pull out all of the bigrams, again, ignoring case, we can see what the most common ones are. ER, as you know, a very common ending. IN, often used as a prefix. TI, ON, TI in suffixes like shun, ON, TE, AT. If we look at the first, but those are bigrams in any part of the word, if we look at the first two character bigrams, CO, UN, IN, RE, DE, these are all common prefixes, things like co-pilot, unfamiliar, incredible, refurbish, dehumidify. If we were to do trigrams, we could also find common three-character trigrams that appear at beginnings of words like STR. If we look at the ends of words, we look at suffixes. So for example, ly in adjectives, slowly, quickly, ponderously. ed as the common past tense for verbs like sorted. So those are things that we can learn just by studying bigrams of, or n-grams of characters. Another example of things that we can do at the character level has to do with rearranging characters or substituting characters. So for example, if we were to ask what are the 10 words that are closest to the string pickle in terms of substitutions, we can use a dictionary lookup for pickle, and then we create a nearest function, and that shows us which 10 words are nearest to this one. So to get from pickle to nickel, we only have to replace one character, the first. Pickle to picked, replace the last. Pickle to picker, replace the last character, and so on. So these often come up, as I say, in puzzles, but this kind of thing can also come up in other cases, like trying to read someone's handwriting. So sometimes you're looking at handwriting, especially if you do historical work. You can't make out all the letters. It's nice to be able to search for a space of possibilities around the letters that you can make out. We can actually plot this with the nearest neighbor graph and see how each of these are related to one another too. So for example, bicker and kicker are separated by a single character, the first character, both of those in the neighborhood, the close neighborhood of pickle. We can also say, well, what are words that start with a P, have a character we can't make out, have a CK, and then some more characters we can't make out, 2 more characters? Do that with dictionary lookup and a string pattern. This might be the word packed, or packer, or packet, or picket, or pickle, or pickup, and so on. Here I'm going to get a list of English words. We can get the nearest ones to pickle again, but now I'm putting the information in the form of a data set. Each one of these words has an index which tells us its position in this list. So the word Dicky, for example, is position 9344 in the list. We can look up a specific word like this. Bicker is the 3224th word in this list. We can also do things like find words based on particular criteria. So for example, if we say, what are the 3 longest words in this list of English language words? 3 scientific terms. And a related problem that we might do while we're exploring characters is to look for anagrams. So for example, if we sort the characters in backward, we get this list, A, B, C, D, K, R, W. If we sort the characters in drawback, we get the same list, A, B, C, D, K, R, W. We can test the equality of these two by using the double equals sign on the sorted forms of the words, and that gives us true. What this means is that it's actually quite easy to create a function that finds anagrams. So for example, what I'm doing here is I'm looking up words that have the same sorted order as the same sorted list of characters as a word of interest. So if I search for anagrams for backward, it takes a second to run, but we find that backward and drawback are anagrams. If we search for anagrams of restful, fluster is an anagram of restful. So this kind of thing, as I say, often comes up in games. For example, if you play Scrabble, then you know that you use this kind of thinking frequently. But it can also be used for doing things like cleaning up optical character recognition too. In linguistics, the study of decomposing words into the smaller units is called morphology. And because there's a lot of different ways to because words are easy to parse out of many natural languages, there's a lot of computational techniques for working with morphology. In English, for example, if we ask for the word stem of running, we get the word run. If we ask for the word stem of inconsiderable, we get inconsider as the stem there. Now, some of these stems are going to be dictionary words in their own right, and some aren't. Let's get a list of random words and a list of random stems. In this sense, what I'm doing is I'm stemming the list of random words. I'm not getting different random stems. We're going to remove all of the cases from this list where the stem and the word itself are identical. Now that I've created this list, I can look up the words and see if the stem of the word is also a dictionary word. So humming has hum as its stem. They're both dictionary words. Vacillating returns vassal as its stem, not a word. Same for jingle, and so on. Chiseled returns chisel as its stem, also a dictionary word. We can investigate how word frequency changes over time. Here are 3 words. Word frequency data will tell us the relative frequency of these words. The, super common word in English, has a very high relative frequency. King, a common enough word, has a much lower frequency. And lily-livered, not a word that most of us use very often, has a very, very low frequency. We can ask to see how a word changes over time. I'm getting word frequency data, a time series, that is a series of measurements, each one dated, and we're going to plot that with date list plot. This shows us the relative frequency of the word veteran, and you'll notice, of course, immediately after World War II, the use of the word spiked. We can look at word frequencies for multiple words. Here I'm plotting war and peace. War is used more frequently than peace. And again, we see spikes corresponding to world wars, but also spikes in use of the word peace. Here's another example, a historical one for audiophiles. The word Walkman frequency. The Walkman was invented in the late 70s, became quite popular in the 1980s. Its frequency goes over time. The Discman, the compact disc music player, starts in the mid-80s, and its frequency sort of parallels the frequency of Walkman, although at a lower rate, and of course both of those terms were eventually replaced by terms like iPod. Now if we plot word frequencies from a text or a large sample of language, we find that the curve has a particular shape, and I'm going to use Alice in Wonderland to demonstrate this. This shape is known as Zipf's law, named after the linguist who identified it in the middle of the 20th century. So I'm counting, I grabbed Alice in Wonderland, the text, I'm doing word counts to count the frequency for each word, and now I'm going to plot, but I'm plotting them with not list plot, but with list log plot, so that this axis here, the vertical axis, instead of counting 1, 2, 3, 10, 11, 12, it counts in such a way that the amount of space taken by the numbers from 1 to 10 is the same as the amount of space taken by the numbers from 10 to 100. What we find is that there's some words, like the, which happen very frequently, but that the second most common word is a bit less frequent, and the third most common word is a bit less frequent, and you eventually drop off to a point where there's lots of words that only occur once, and lots of words that only occur twice, only occur 3 times. This shape, this curve, is known as Zipf's law, and occurs not only in natural language, but in a number of other situations.